Hello everyone, we are ESET researchers and a lot of time working with complex thread. I am Aleksandr Matrosov, it's Eugene Rodionov, and today we're presenting about Gapz. It's a really interesting and complex bootkit. It's used many interesting tricks and exploitation. And the outline of our presentation, starting with the Gapz dropper, and we described interesting code injection trick with explorer.exe, continue with bootkit details, and Gapz used really interesting technique for infection volume boot record, modify only one word, 4 bytes, and receiving control to the shellcode. Continue with Gapz payload, and the next it's forensic approaches, and the last words of our presentation is the part which described our plugin for hex-race decompiler. This plugin is really helpful for independent position code analysis and helpful for object-oriented code reconstructing. Okay, starting with the Gapz dropper. Gapz dropper based on Probl loader builder. This builder is science sprayed from September 2012. Code is already leaked on the public, and at this moment I know 5 malware families which use this code for distributing. And this builder used really interesting trick for code injection. If you try to analyze the samples with these droppers, you can recognize Probl loader by these import tables. And more interesting part about the dropper code injection to explorer.exe, because used interesting arbitrary code execution into Explorer process. The first step is injecting to Explorer.exe some shellcode. On the next stage, executing code for privilege escalating under trusted process address space, and after that, starting infecting the system process. Shellcode have 2 stages. On the first stage, the dropper executed on infected system, opens the shared section from explorer.exe base name object, try to open one from this list, and after that, copy shellcode into this shared section, and shellcode search the window shell tray VND, and call the WinAPI function getWindowLong with index 0. It looks like this. And the dropper calls getWindowLong on the first figure. And the next set parameter to modify window-related data. And after that, the next step, call the send notify message for triggering the shellcode. It's a really interesting trick, because Explorer.exe process working with active user privileges and open for some modification under this user account. And some security software have this process in whitelist, and our shellcode executed in trusted address space. And on this figure, you can see the vulnerability into explorer.exe process. It's arbitrary code execution, but it's not typical. It's not fixed, and Microsoft not recognize this code as vulnerability. But many malware already use this trick for distributing. Okay. Send notify message transferring control to the address pointed to address in user APC dispatcher routine. This routine is hooked by dropper and transferring control to the next stage of shellcode execution. This stage uses rob gadgets to jumping into shellcode memory region and bypassing the deep and assay layer, but on yesterday talks, Elias discussing about emed 4.0. I guess it's blocked this code for executing on 86-bit systems. And the last step is into address space explorer.exe executes the jump instruction with the address of the shellcode. It's the call graph from reconstructed algorithm of execution shellcode. The third stage is configure the shellcode data. Next, hook the user APC dispatcher and search the drop gadgets. And other function, it's some helpers function for us. Disassembler engine, Gapz, and power loader used hacker disassembler engine. It's open source and accessible for public. And last stage, triggering the shellcode execution for call API function, create thread with new process of dropper, new thread with dropper, and it looks like that. Yeah. And on the right side, the figure described restore set window long to original state after shellcode is executed. Let's fix it. And we continue our talk with details about bootkit. Eugene.
Thank you. So in the next slides, we will consider the bootkit implementation and the rootkit functionality of Gapz. Before we go any further, consider our classification of the modern bootkits, which are based on BIOS. We're not speaking here about unified extensible firmware bootkits because they have different approach. So all the bootkits so far seen in the wild may be split in two broad categories. The first one targeting MBR, master boot record. The other part infects VBR. The MBR bootkits itself can infect MBR code as TDL4 or other widely spread bootkits does. Or on the other hand, they can modify partition table. For instance, Almaska bootkit, it creates its own partition table entry, marks it as an active, and writes its malicious code in this partition. But the MBR code remains untouched and is not modified. So it's more difficult to spot in the system, this infection. The other infections, which are referred to as VBR or IPL, are very interesting as well. There is an IPL code modification, which Rodionov does. It modifies the initial program loader code, which is not the VBR. This is the 15 sectors which are following VBR, and it is as well very difficult to spot. And there is another class of bootkits which modify BIOS parameter block, and this is where the Gapz is. So the Gapz modifies the BIOS parameter block, and it leaves MBR and the IPL code and VBR codes untouched. The main purpose of the bootkit is to load malicious unsigned kernel mode driver. To achieve this, it's used rather standard approach. It starts with hooking interrupt 13 handler, which is used to access the hard drive, to read or write the hard drive. So being able to hook this interrupt handler, the malware intercept read requests from the hard drive and modifies the following modules: NTLDR, boot manager, winload, and kernel. One of the most important things to do while the bootkit loads is that it should retain control between the execution environment processor mode switching, because it starts booting at the real mode and then continues in the protected mode. So the bootkit host has to retain control, because when the execution mode switching happens, the whole memory layout is completely changed. And the malware also patches kernel and winload.exe to disable Microsoft kernel mode code signing policy protection to be able to load it assigned malicious kernel mode driver. So here is the graph which depicts the process of the bootkit process. It starts with hooking interrupt handler 13, and then it waits until boot manager is loaded. As soon as the boot manager is loaded, this routine is patched. It patches just by modifying binary base. And here, this routine waits until the winlaw.exe is loaded. As soon as winlaw.exe is loaded, this routine is hooked in the winlaw.exe, which in turn is used to wait until the kernel image loaded. And one more interesting thing to pay attention here is that this hook is triggered in the real mode, while this one is triggered in the protected mode. So patch and winlaw.exe is used to disable integrity checks for kernel and to be able to retain control after switching into protected mode. And finally, when the kernel image is loaded, the EONE system routine is hooked, and the malware waits until this routine is executed, and as soon as it returns control to the bootkit, the malware proceeds with loading malicious kernel module. Some of the most interesting features of the bootkit is that it results in modifying only 4 bytes of the VBR. And here, at the bottom of the slide, you can see the VBR layout for Microsoft NTFS volume. There are 3 bytes. The first 3 bytes are instructions, which it transfers control to the VBR code. There is a BIOS parameter block here, a special structure which describes the volume partition, some error strings, and the signature. So the malware modifies 4 bytes here, and the thing is that these bytes might be different on different installations and on different instances of the operating system. So it's not straightforward to dissect this modification, because on different systems, these 4 bytes are different. And here is the structure which describes the BIOS parameter block. This structure is very specific to particular volume, and this structure is presented for NTFS volume. And the highlighted field, you can see the hidden sectors, and this is the field which is modified by the bootkit. On the screenshot, you can see the layout of the VBR. So this all is the VBR. The VBR code of the active partition is here, and the hidden sectors field is here. And the highlighted bytes with the red color is exactly the bytes which are patched by the malware. And we can see that almost your other part, the VBR code remains untouched. It's not modified. So let's discuss the meaning of the hidden sectors field. At the top of the slide, there is a layout of the NTFS volume before infection. And the hidden sectors provides offset from the beginning of the hard drive to the initial program loader stored on the hard drive. This offset is provided in sectors. So what happens when the system is booted? The MBR is loaded, the MBR code looks for an active partition, and the MBR code reads, loads in memory the VBR of the active partition and transfers control to it. The VBR code reads a few sectors starting at offset hidden sectors and transfers control to it. So what happens when the system is infected? The infected VBR contains hidden sectors which provide offset to bootkit instead to the initial program loader. And as a result, when the system is booted the next time, the VBR code loads bootkit sectors with the bootkit code instead of the initial program loader. So that's how the bootkit is triggered. As soon as the bootkit receives control, it survives several steps and finally loads its kernel mode module, which contains the rootkit functionality. So the next slides will deal with the rootkit implemented in these Gapz. It is very interesting, very rich functionality. The main capabilities of the rootkits are the following. It provides the hidden storage for the payload and configuration information downloaded from CNC servers. The user mode payload injection to inject payloads into the address space of the processes. It provides the cover channel to communicate with CNC server and stay on the radar of personal firewalls and network monitoring tools. And it provides some authentication primitives to authenticate CNC servers. The rootkit functionality is implemented as position-independent code, which is available both for 32 and 64-bit operating systems. And here is how it is implemented. There is a global context, which is allocated at the very beginning of the initialization of the bootkit. And there is a hexadecimal constant, BBB, which is substituted with the pointer to this global structure during the initialization. And as a result, we can see that, for instance, the call to open key is performed in the following way. So this variable, in fact, points to the global context, which holds all the necessary data which are necessary for bootkit to run, data, a pointer to the imported routines, the entry points of the exported routines by the rootkit module, sorry. The position-independent code consists of a set of blocks. Each block implements its own functionality. On the next slide, we will describe the functionality of these blocks. Each block starts with a header, which describes its position in the kernel multi-module. There is a procedure base. This integer is used to calculate the entry points of the routines which are implemented within specific module block. There is a next block of set to navigate through the blocks within the kernel module. There is a block initialization routine which initializes the block, and a set to the configuration data. There are exactly 12 blocks implemented in the malware with specific particular functionality. The most interesting blocks are maybe seen here. For instance, it implements very rich cryptographic library. There are streaming ciphers, block ciphers, hashing algorithms, encoding algorithms, and even asymmetric cryptography, which is based on the elliptic curves for authenticating CNC server. It contains the hooking engine to set up hooks in kernel mode, a disassembler engine, the hidden storage implementation, self-defense mechanisms to prevent from detecting and removing the malware from the system. There is a set of blocks implementing network communication. You can see here. There is a data link layer, custom data link layer, custom transport layer, which contains TCP/IP protocol implementation, and the protocol layer, which is a HTTP protocol. It contains a very interesting payload communication interface to communicate between the user mode payload and the kernel mode component here. And the final block contains the main routine which runs the bootkit. In fact, it is a loop which just connects to CNC server, requests the payload, reports to CNC server on the status of the bot, stores the payload in the configuration data, and injects the payload into the processes. The first thing we will start with discussing the hidden storage implementation. The hidden storage is a FAT32 hidden volume which is based on the source code of the full FAT project. This is our open source implementation of the FAT system for embedded devices. It is a bit modified full FAT system in that the entry of the file in the file directory table is 32 bytes, while in the conventional FAT specification is limited to 11 or 13 symbols. So as seen on this screenshot, there is a directory table here. We can see some modules here, the payloader or plugins and configuration information. And it takes 32 bytes, so the conventional FAT parsing tools will not work in this case. The hidden volume itself is stored in the file system with this name. These data are generated based on the configuration information of the malware. This file is accessible from the user mode, but if you try to open a handle on it for reading, you will get sharing violation error, what means that the malware holds an exclusive handle on this file. Another thing is that the contents of this volume is encrypted with the advanced encryption standard with 256-bit key in CBC mode, almost like in the industrial volume encryption tools. Here is the code decompiled. The initialization value, which is used for CBC mode, is the logical block address of the particular sector. So it encrypts sector per sector. And even though the same key is used for each sector, it results in different cipher texts since the different initialization values are used. The next slide covers the Gapz crypto library implementation. As it was mentioned, it contains very rich cryptographic primitives, hashing algorithms, the ciphers like RC4, Randall, which is the advanced encryption standard, and it contains even the custom implementation of the elliptic curve cryptography encryption scheme, El-Gamal, and this asymmetric crypto is used to authenticate replies from CNC servers to prevent receiving commands and payload from the not authentic CNC servers. To be able to protect itself from being removed from the system, it hooks the RPMG internal device control, which is a de facto standard in the modern rootkits targeting Microsoft Windows platform. It hooks the following handlers and is interested in these requests. It monitors these requests to protect the MBR or VBR of the system to be read or overwritten. We can see here the MBR because one of the earliest modification of Gapz we spotted was MBR based. And this talk was concentrated mainly on the VBR because this is far more interesting. And it protects its image, the kernel module on the hard drive from being overwritten. It hooks the routines by patching the first bytes of the routine, but the interesting thing that it tries to avoid patching the routine at the very beginning. It utilizes hacker disassembler engine to disassemble the routine and to skip such instructions as a no movie DIDI in the very beginning of the code, as shown here. And here is the screenshot from Windows Debugger. So we can see here that the jump instruction is placed here, not at the very beginning. So we believe it is done to maybe increase the stability of the infection or make the hook more difficult from being removed. And this slide is about the code injection functionality in the user mod address space of the processes. Well, it's very straightforward and quite, it's not as elaborate. The buffer is allocated in the target process. This buffer is written with the malicious image, and the remote thread is created, which runs the loader code to load the payload, to initialize import address table, to fix relocations, and etc. So there are 4 loaders. 2 of them are dedicated for DLLs, and 2 of them are dedicated to exe images. The DLL loaders are mainly deal with the payload, with the plugins. Here is the export address table of the plugin. It exports 3 routines by ordinals. The ordinal 1 is for initializing, like here, loading. The ordinal 2 is for unloading plugin here, and the ordinal 3 is executing commands in the user mod address space. Further on the slides, we will see an implementation of this routine for executing commands on, based on the one of the plugins which goes with Gapz. The 2 exe loaders are, the one is very simple and straightforward. It just drops the payload in the temp directory and runs the process. The second is a bit tricky. It creates a legitimate suspended process like Internet Explorer.exe or svc host.exe, and then overrides process image with the payload image, fixes the thread context so as to EIP register points to the entry point of the new module, and then the process is resumed. So let's talk about the Gapz network protocol implementation. There are two ways the malware is able to communicate with CNC server. The first way is to use the plugin Overlord 32 or 64, which is injected in this, let's say, host.exe. The malware transmits the message to be sent over the network to the plugin, and the plugin sends to the CNC server using Windows socket implementation. And the second way is to use custom protocol stack implementation based on the NDIS mini-port driver, which is stealthier and difficult to detect by personal firewalls and network monitoring tools. Here is the architecture of the network protocol implemented in Gapz. There is a data link layer implemented based on the NDIS, the custom TCP/IP protocol implemented in block number 9, and the protocol application layer is in HTTP protocol implemented in block number 10. And let's look how Gapz sends the packets to the CNC server. So it is able to obtain the lowest device in the NDIS driver stack. This is a mini port adapter driver. This is the bottom. This is the most bottom device in the driver stack, and the Gapz sends packets directly to this mini port adapter driver by passing protocol drivers, filter drivers, and intermediate drivers. A lot of software, which is a security software or personal network monitoring tools, they operate at the filter driver or protocol layer, and therefore the malware is able to stay under the radar of these tools. Definitely, the communication may be the communication of Gapz with CNC servers may be spotted using the firewalls which are installed on gateways or something. But the personal software, for instance, host intrusion prevention systems, will not spot this communication at all. The main capabilities of the protocol are the following. It's able to download the payload, report on the status of the bot, the payload which is run on the system, and request configuration information. It employs HTTP protocol and sends request-specific data in post method. And here is how the message which is sent from the malware to CNC server looks like. There is a dynamically generated HTTP header. For instance, here we can see that all the fields are generated dynamically using a set of the predefined values like use region string, content disposition, content type, to make it difficult to detect by using signature-based approach. And the message header, the message starts with the message header. The header starts with the 128 randomly generated bytes. Then it is followed by the integer, and we believe this is the version of the payload. And then it is followed with the 64 bytes randomly generated. This is a so-called authentication string. And then the message header is followed with the request-specific data. And here is what the malware receives as a reply. The message starts with the encrypted RC4 key1. And this key is encrypted using elliptic curve cryptography encryption scheme. So the first thing the malware does, it decrypts key1 using private key, which is instantiated within the malware body. As soon as it obtains the key1, it decrypts the rest of the message with RC4 cipher with key1, and then checks authentication string with that one which was sent previously here. If the string match, then that means that the data came from the authentic CNC server and the malware processes the reply. Otherwise, that means that someone is trying to send fake data to the malware and it just rejects. To be able to reach CNC server, the malware tries to approach it in the following way. There is a second-level domain name in the configuration information and a list of third-level domain name prefixes listed here. And the malware runs through this list and concatenating this prefix with the second-level domain name obtaining domain name and trying to contact CNC server using this name. If it's reachable, it stops and using this domain name to communicate with CNC server. And here is more domain names which are obtained from the other version of the malware. So there is a plugin which goes with Gapz, which is dropped by the dropper. This is Overlord 32 or 64. This is essential part of the malware. It is injected in this, let's say, host.exe process. And it's responsible for dispatching the following requests. The first, it sends and receives data from a remote host using Win circuit implementation, as was discussed before. And it gathers information on the presence of the particular software in the system. It is interested mainly in the security-related software, the antivirus products, the HIPS systems, network monitoring tools, system monitoring tools. It contains a list of hashes of names of the security products, and it runs through the. It obtains a list of all the processes running in the system, calculates hashes of their name, compares these hashes to the table it has in the configuration information, and in case there is a match of the particular hash, it sets up a specific flag. And these flags are sent to CNC server. And here about the Gapz user mode payload interface, which is used to communicate between the user mode payload and the kernel mode driver. To construct this interface, the malware modifies null.sys driver. On the left-hand side of the figure, you can see how it looks like before patching. There is a driver object, and the driver image in the memory. The driver unload routine points to the corresponding driver unload routine in the memory, and the handler of the device control request points to corresponding handler in the image. What happens when the malware runs in the system? It sets driver unload to null, what means that this driver cannot be unloaded anymore. And the device control handler points to the driver unload routine instead to its original handler. The driver unload routine is hooked. The hook transfers control to the dispatcher code here. And here the malware decides whether it should process the request on its own or transfer control to the original handler. Here is the decompiled code. We can see here that the request comes from the user mode payload encrypted using RC4 cipher. So the first thing, the handler decrypts the payload request, checks signature to ensure that the request goes from the payload. Then an appropriate handler is executed here. And finally, the reply is encrypted again and sent to the user mode payload. And as a conclusion of this section, here is the table which summarizes some features of the most widespread, widely known bootkits in the wild. And we can see that the Gapz is very advanced due to its custom TCP/IP network stack implementation, rich crypto functionality, and the VBR infection. So in the next slides, Aleksandr will describe forensic approaches to Gapz.
Yeah, Gapz is really interesting threat, and we already researched it a few months and prepare some special tool for forensic approaches this threat, because it's not so easy for forensic engineers extract the hidden file system and extract the files with CNC domain names and shellcode modules, because for extracting the hidden file system files, you need to reconstruct full structure of hidden file system and encryption algorithm. In the last year on REcon, we already present a hidden file system reader. It's a special tool for dumping, for extracting hidden file system of most known bootkits and other threats which used hidden file system partition or hidden containers. This tool can extract the Gapz and all known bootkits. And of course, this tool can extract infected MBR and VBR, because we have anti-rootkit engine in this tool. How example, it's the dump of Gapz with MBR, but with volume boot record infection looks most interesting because a lot of shellcode and a lot of modules. It's tool already released on public and you can download for use. Not with sources, but binary is for public, for free. And we continue our talk with the part of some C++ code reconstruction problems because it's so related with code-independent reconstruction problems. And the last section of our talk will be some plugin for help to reconstructing object-oriented code and code-independent, position-independent code. It's the list of some problems. The first, of course, it's object identification because it's working for manually recognized the object and identify. Class layout, identify constructor, destructors, and reconstructing RTTI objects. And it's depend on compiler design, and each time you need recognize how this code is compiled for this compiler. About RTTI reconstructing, many words already presented on the last year REcon by Igor Skachinsky from Hexrace, and we not repeat this stuff. C++ code reconstruction, it's not so easy, and each time it's really hard manually work. And if you look the Stuxnet or the Flame, it's really big and huge code, and you need to reconstruct so many objects and other stuff manually. How example, it's smart pointer structure from Flame, and it's assembly code presented here, and after some manually work with structures, it looks like really beautiful and short. Other example, it's virtual function identification. It's from spam bot Festi. You can see this code, and in assembly language, you need to recognize the virtual method, exact virtual method, but virtual table is so huge, and statically, you need to calculate the exact index of virtual table, but sometimes it's really hard to recognize statically. Other primer with huge virtual table. It's from Ronix, RC4 get buffer size. It's really short and really nice look after manually work, but you need this such hours do this. Constructor identification, yeah, it looks good. But how you do it manually? In our case, we used Hexrace decompiler and add local types with C structure for each object, and sometimes it's working good, but sometimes we need do some dynamic analysis for calculate exact calls in virtual tables. With huge virtual tables, it's working not so good. How example, take this virtual table and manually reconstruct, looks like this. We add in IDA C structure. It's this structure describes the object. Yeah, it's good, but you do this work only manually. After this, it looks like this code. It's really beautiful and really nice look after manually work. And next part of our presentation, we present the Hexrace Code Explorer. It's a special plugin for Hexrace decompiler, and this plugin helps for reverse engineers to do this manually work. Okay, Eugene, your move.
So in this part, in this final section, we are going to present what we've done during the analysis, because analyzing Gapz and other complex malware such as Sax and Flame, Jigu, which are there is a lot of abundance of the object-oriented structures, motivated us for developing which could allow and facilitate analysis of the position independence and the object-oriented code. We choose Hexrace because it was very handy tool for our decompiling and analyzing, reversing the code. It saves hours of work. So the first thing which we are implemented here and which really helps us to approach this problem, it saved us many hours of manual work, is to navigate through the decompiled virtual methods, as it was told by Aleksandr on the previous slides, and to partially reconstruct object types. We mean partially because the plugin is not very good with the obfuscated code, but it is intended not to work with the obfuscated code, but with the code which is produced by their industrial compilers like Microsoft compiler, which has like a C++ structures. And sometimes due to the semantics, it's very difficult to have the exact representation of the type in the C structure. So before presenting the plugin, here is some background on the Hexrace for those who are not really familiar with this decompiler SDK. So in the heart of this decompiler, there is a tree structure, which is a syntax tree, which can be seen on this slide. For instance, the expression variable 3 equals variable 2 plus variable 7 is represented in Hexrace in the following way. There is a node which is a CITMT object of this type, and there is an assignment which is equal sign addition here plus and variable 2 and variable 7. So this is the way how the Hexrace internally represents the data. And why we choose Hexrace? Because we are given access to this syntax tree. We don't have to build its own tree because Hexrace do a lot of work, hard work, to build from the assembly code this nice representation. This tree is built during several iterations. There are 9 iterations, so equal 9 maturity levels. We use the final maturity level, which is ready to use, but if you need access to something or like intermediate maturity level, you can get access to this tree at this level. So the CITEM object, which is a node in this tree, is a base class for expressions and statements in the C language. So expression is everything what has a type. So there is a type information attached to the expression. For instance, we can see here the following expressions types: assignment, integer, variable integer, call, which returns the integer value, and the routine, which is called here. You can do whatever you want with the C tree structure, but you have to keep one condition. You have to keep the type information consistent. I mean, for instance, if the call needs the word, then this routine has to return the word as well. And this segment int, so these are the same. So you have to preserve the type information during your transformation, but you can transform this C tree structure as you wish. The statements they may be blocks, branching like while, do, switch, return, assembly, inline. And the hex trace provides you with some iterators which allows you to go through this C-tree structure. There is a C-tree visitor, which is a base class for C-tree parentee. And this iterator preserves the information of the parent of the node which is visited at the moment. And now let's have a look at the implementation of the position independent code in Gapz. So we can see here that at the very beginning the buffer in kernel mode is allocated here. Then this buffer is filled with some data, the pointers to the imported routines, some internal routines, configuration information, and etc. And finally, this context is used here, like this one. So what we would like to have? We would like to have a handy tool which allows us to automatically reconstruct the type, this type, based on the pointer to the instance and the initialization routine. This is the first thing. And the second thing, we would like to have a nice navigation in the hex decompiled codes. So we use the local types in IDA to represent the objects, for instance. We reverse this routine, reconstructed this type, use hex trace to represent this type in this way, named fields, so now it looks like more easy to comprehend, more easy to analyze, and it saves time. And to be able to have a navigation through the virtual calls, we can do it easily using the C-tree structure. So if we encounter a call here, we can go down this branch and find that there is a global struct here, for instance, the pointer to the global context here. It is here and it has type struct IP thread 1. Then there is a reference to the field at offset 8 integer field, this one, prods both 3, which has a type struct IP thread 23 here. And finally, there is a reference at offset 12, integer as well, this hook routine, which is then casted to this type and then called. So we would like to have a nice way to navigate in this function, because the decompiler, it doesn't know nothing about this function but its name, because we provided its name in the previous slides. The hook routine is this one at offset 12. So, and it's time for a small demonstration here. Is it okay? Can I see the code? Okay. So let's go to the initialization routine for block number 2. This is the crypt implementation here. So this is actually the object which we reconstructed manually, and we can find this object here. Yes, this is what was reconstructed manually so far. And here we have references like the internal routines which are initialized using these values. So we pre-computed these values before and we already know how it works, but we have a plugin for Gapz which does it automatically. And this is fields. What we do is just navigation for the convenience. We double click on this routine and we go directly here, which is it's very convenient. It saved a lot of time for analysis, because the hex trace decompiler doesn't provide this functionality. And this is for instance, for position independent code here. For instance, for object-oriented code, we can automatically detect the virtual table and fill this address with the virtual table, so the navigation will be very good. So we can go, for instance, the implementation of the elliptic curve cryptography algorithm here and navigate through the routines like as even though it is like a normal routines here. But in fact, it is a field in the structure. You can see it is in the field in the structure of say 15 hexadecimal. just display the graph, which is like a C3 structure for this routine. The highlighted is the node which we have chosen here. So yes, there is a variable 5 here. And then this field is referred, so we know that there is a reference to this field at offset 192. We go to local types, which we know. We find this field at this offset 192 and obtain a trace either from here, or we can have a custom database with the addresses corresponding to the field structures to have this navigation. Another thing that saved a lot of time for us too is the reconstructing types using this plugin. So we would like to have something that receives as input the pointer to the instance of the object and its constructor or initialization routine. And as output, it would give us a C-like structure object representation. It can be done using hexrace plugin. For instance, to be able to do this, we have to monitor the following expressions: the memptr, which is a reference to the particular offset in the structure; the idx, this is using the index; memref, this is just a reference in some address within the buffer; and there are some modifiers here. For instance, the helper functions, which gives us a low byte or high byte, load word, hide word, low word, high word, and etc. For instance, we can see here that there is a variable A2 pointer, which has an offset 100, this EO control hook array, this memptr. Then there is an index offset here, and there is a segment of the result. So this is a constant. And let's have a demonstration, one more. For instance, for the same block. Supposing we just given we have this type reconstructed manually, but we just, in case of id, it will just not produce integer like this. So yes, it provides now no information about the structure, and we want to reconstruct it manually. So what we do, we just have a reconstruct type and have it here. Yes. So here is, we just counting the references at particular offset, find which fields are referenced and how they are referenced, and then we will build this structure, which has these fields. And then we can use this structure to like rename and rename the fields based on their meaning. But this is very handy tool, or for instance, for analysis such as Flame or Stuxnet, because there is a lot of object-oriented code and there is a lot of constructors. And when you just go into constructor, you see memory allocation operator. There is a pointer to the instance. And yes, so this, it just saves time, very convenient. So this is how it looks. Yes, and Aleksandr is about to conclude our talk.
Good news, Hexrace Code Explorer is the open source plugin and will be released after Hexrace plugin challenge on the GitHub. And now we have open beta testing. If you want, you can call us by email. And we provide the binary for some feedback or feature requests. Hexrace Code Explorer support 86-bit platform and ARM, and developed fully on C++, because Hexrace SDK don't support Python, and it's a lot of fun with Hexrace SDK in development process. It's the references on white papers and blog posts about the Gapz. We already released a really huge 50 pages white paper about the Gapz bootkit and described all tricks, all techniques used in this malware. Be smart with ESET, and ESET hiring the talented reverse engineers to Montreal lab. If you want, call us. Thank you for coming, thank you for your attention, and if you want, provide some questions online or after talk by Twitter, follow us. Thank you.
If there are any questions.
So how long did it take for your intelligence system to flag Gapz, and what is it about Gapz that made it pick up? And how long was it undetected before you all got a hold of it?
Okay, it's a good question. We have some cloud system for our product, and we recognize we collecting information about boot sectors, and we recognize some anomaly boot sectors, and collect more information and find the sample in our sample system. Yeah, it's the way how we recognize this threat.
How long was it in your system before you recognized a particular, I guess, get boot sector pattern that was being?
I don't know this.
Okay.
Yes?
Do you have to boot another OS protect or
No, we didn't uncover any other bootkits which employs the same functionality. Like the same approach. The question was if we are aware of any bootkit which employs the same approach. No, we didn't have to boot on the other system to detect this malware, because there is some anti-rootkit functionality which allows us to be able to read the original sectors and to get to spot this modification on the infected system.
Could you repeat the question? Negative offsets?
Well,
okay.
Yes, well, we don't encounter these negatives offsets so far. This plugin was developed mainly for object-oriented structures. Sometimes, yes, we encounter, sometimes when there is a nested type, a nested object, and we refer this object in the using the negative offset to obtain its base object, well, we just keep this information and try to figure out just the what's the parent of the object.
Yes, please.
You mentioned Basilani's talk on Emmet and how I didn't catch the whole thing here, but you were somehow saying that Emmet was proactive defense against some of the return object-oriented techniques that were used by Gapz. Do you think, now that we know more about Emmet, that it would have been sufficient had Emmet been?
Gapz used really pretty easy technique with ROP, and it's possible to block with Emmet. Yeah. Elias described yesterday a lot of stuff about Emmet, and after that, I think yes, it's blocked by Emmet.
So, if there is no question, thank you for your attention.
Thank you.